Hi everybody. It is Mrs. Zaring talking to you from the past. We're going to do a video lecture today since I am absent and out of class. So if you have not already done so, will you please turn to page 77 in your workbook. There is a note taker called position, motion, origin, and speed that we are going to be going through in class today. So we get to start a new unit, which is really exciting. We're out of measurement. We now know how to do dimensional analysis. And just as promised for the first quarter of the semester, we get to start learning about physics. So the beginning of physics, we first have to understand what is motion. So just to give you a little synopsis of what's going to happen in these next couple units is we have we're going to talk about, in this unit specifically, speed and acceleration in terms of motion. And then in our next unit, we're going to talk about forces and Newton's laws. So it just kind of shows you the direction that we're headed. So let's talk about motion starting today. So we got to know how something is moving in order to better understand it. So there's a couple of key terminologies that we're going to go over here in the beginning. One of them is thinking about what your position is in the world, in the room, what an object's position is. So for example, some of you have spent very little time in Boulder High School, so this might seem even more abstract, but let's think of either Boulder High School or previous school you've been at, and I blindfold you. And I plop you somewhere in the middle of the school. You have no idea where you're at. And I tell you, I want you to find the auditorium. You're going to come across a problem because the first thing that you're going to have to solve and figure out, is where am I? And how does the place I currently am compare to the location that I'm trying to get to? The auditorium. And that's what we're talking about today when we talk about your position and how you are moving. So, this is what a position is. It is a place of an object that's always measured relative to something else. And that something else is typically what we call an origin. So, here's some examples of what a position is. I could talk about the position of my car in the Boulder High School parking lot right now, being 3 cars to the left of the BMW. I described the position of my car in relativity to another car in the parking lot. Another example would say, if I'm sitting in the auditorium, I could say I am sitting on the 3rd level, 4 rows back from the front. So I gave my position relative to the location of the front of the auditorium or a stadium, let's say. My third example is, let's say I'm talking about my house in Boulder. And I'm going to say my house is 3 blocks east of the 29th Street Mall. I gave a position relative to another street, another location. And I gave directions, and I gave how many blocks you needed to go over in order to find my position of my house. And so I said something in the last slide, and I said that position is relative to something we call an origin. You may have heard the term origin in math before. It's a place where your position has maybe been given a value of 0. We talk about the origin of a graph being the center at 0, 0. And in science, we also define the origin as a point that all other positions are measured relative to. This could be on a graph. This could be a position in the hallway, in a stadium, just as much as the examples I did on the last slide. But the origin is whatever you're assigning the value of 0 to. It doesn't have to be on a graph. You're just saying that is my origin, that's my starting point. And if I have to assign it numerically, I'm going to assign it the value of 0. So let's talk about this in terms of where you sit, perhaps, in our classroom. So I know some of you have never sat in our classroom, but just sit here and imagine that you could be sitting in a classroom. And remember, you have a position. It's relative to something. Think about where you might be sitting in a classroom. You have a series of desks. They're usually lined up in rows, in columns. You could probably easily describe your position in the class relative to where you are. So let's say we're in our classroom here. 0 is the back door, for those of you that are sitting in here or have been in our classroom before. 0 is where the back door is. That's the origin of the classroom. This is going to be the front of the classroom, and we have our seats arranged by rows 1, 2, 3, 4, 5, 6, and by columns 1, 2, 3, 4, 5, and 6. What I want to know then is, if I asked you to move to seat 5-2 from seat 2-6, how many seats on the x-axis, remember moving back and forth horizontally, or how many seats on the y-axis would you have to move to go from one seat to the other? So pause real quick and discuss. Okay, welcome back. So you would have to, on the x-axis, if you were starting at seat 5-2, move over 1, 2, 3 seats. And on the y-axis, you would have to move up 1, 2, 3, 4 seats. We can also talk about, not just in terms of up and down, but we can talk about position and origin in terms of coordinate systems. So you might be familiar with this if you look at a map of Boulder. We have a coordinate system that go by streets. We have streets up and down that go by numbers. So if you think about Boulder High School, we're on 15th Street. Then you might also think about our other going the other direction. Typical Boulder streets we have is Canyon, Walnut, Pearl. We exist on 15th and Arapahoe for the school, but that's what we call a coordinate system. There are probably a lot of other coordinate systems that you've seen before, but this is how I would define this. The coordinate system defines the location of a point on either a planar or a spherical surface. By planar, I mean flat. Spherical, I mean round. So other than a map of the city of Boulder, I can think of a couple other coordinate systems that we use in society. For all of my sports fans out there, we use coordinate systems when we talk about a football field. We mark it by yards to measure where someone might be on 1 yard line on the starting line to a stopping line. That would be an example of a planar coordinate system. We also talk about a spherical coordinate system when we look at the latitude and longitude of our entire globe. So the origin in this case, the starting point would either be at the equator or the prime meridian. And then you look at latitude or longitude to describe your position in relativity to either the equator or the prime meridian. So equator if you're talking about latitude, prime meridian if you're talking about longitude. So if you're talking about Boulder and you're saying I live in Boulder, you'd say you live at 40.01 north and 105.27 west. That's your latitude and your longitude in terms of the spherical coordinate system. Then we get into the fun stuff. This is what we're talking about when we're talking about physics, is distance. So not just a position in relativity to an origin. Now we're talking about distance, how far you are traveling when you're in motion. The difference between a starting, a beginning, and an ending point. So let's go back to our example of the coordinate system on a football field. I might say that I'm going to start my play on the 30-yard line, and I'm going to stop, I'm looking at this, at the, I'm so bad at sports, 30, and then this is 20, so this must be the 25-yard line. Okay, there we go. 25-yard line. I don't think that my lines are matching up very well, just excuse that there. Okay, so my lines didn't super match up to what I was actually trying to describe, but let's say I'm starting on the 35-yard line, ending on the 30-yard line. Either way I described it, you have a distance of 5 yards, the difference between my starting point and my stopping point. Unfortunately, with that football play, they didn't get going very far. So, distance, the difference between your start and end point. This one's a little bit of a better example. Let's say we have a car that's running down a track. At its origin, the starting point, we're going to assign the origin to be at 0 centimeters and the current position of the car to be at 50 centimeters. Therefore, the difference between my starting and my ending point, my distance, is 50 centimeters. Now, speed gets to use distance in action. Speed refers to the distance that you can cover within a certain period of time. So we use a general unit of distance divided by time, distance per time. And they're definitely units of speed that you have used or heard of before. When we are driving a car here in America in the English system, we use miles per hour. You might also talk about meters per second, kilometers per second, or kilometers per hour, and lastly, feet per second. Any unit of speed, a distance covered in a certain period of time, is going to be given some unit that is a distance, like miles, meters, kilometers, or feet, divided by time, like hours or seconds. So if speed is a distance covered in a certain period of time, you're just really looking at exactly how far you traveled and how long it took you to get there. So let's say I was taking a road trip, and when I started out versus when I stopped, it took me 1.5 hours to travel a distance of 150 kilometers. I'm traveling around Lake Michigan. Maybe I'm going to go see Mr. Sullivan's family. If I'm going to take my distance divided by time to calculate my speed, I'm going to take 150 kilometers divided by 1.5 hours. When I simplify 150 divided by 1.5, I get that the average speed that I was traveling at was 100 kilometers per hour. Now, this doesn't mean that the entire time I was traveling at exactly 100 kilometers per hour. This is really looking at my average speed over the entire distance that I traveled, which if it took me that much time to travel that long of a distance, I would have had to travel 100 kilometers per hour in order to get there. So, there is a difference between what we call speed and what we call velocity. I hear these terms used synonymously so much, but I am here to tell you that there is a difference between the two. When we talk about speed, it is just distance divided by time. How fast something is going. You could be, going down 36 on your way to Boulder, and you'd be going 60 miles per hour if you're following the speed limit. But a velocity describes speed, displacement of time, also with a direction. So if I was traveling, again, if I'm traveling down the 36 highway and I'm trying to get to Boulder, I would say that I'm traveling 60 miles per hour west, with my velocity including a direction in terms of west. The equations for the two look very similar. You have speed is equivalent to distance divided by time. Velocity is also distance by time, but when you record velocity in an answer, you must include a direction. So again, let's say I'm traveling down my football field again, and let's say I'm going from the 3-yard line to the 5-yard line, I'm going to be traveling at 2 yards per second. But if I'm going the other direction, and I'm going from the 5-yard line to the 3-yard line, I would be moving negative 2 yards per second. The reason for that being because I'm moving in a negative direction. So, we're going to talk about how to manipulate the speed equation. Now, if you aren't like super comfortable with algebra, it's okay, because at the end of this, ultimately, I just want you to know what the 3 different equations are for knowing speed. I'm going to show you algebraically how we get there. I want you to follow along so that you can understand the math that is going into this. But at the end of the day, I will not ask you to algebraically rearrange these. You will have the equations to use on your practice problems. So the normal speed equation tells us that speed is equivalent to distance divided by time. We really can simply write that as S equals D divided by T. So simplified, S equals D over T. Done. The first one is easy. Now let's say I was solving a word problem, and in the word problem they give me time and they give me speed, but I want to solve for distance. How can I simplify this equation so that distance is alone on the equal sign? So if I start out with my normal equation, speed equals distance divided by time, I really want to get what I'm solving for by itself, and I'm trying to solve for distance. So if I multiply each side by time, then on the right-hand side of the equation, time is going to cancel, and I'm left with an equation that distance is equivalent to speed times time. Now let's say I'm given distance and speed in a problem, but I want to solve for time. How could I rearrange the equation to get time isolated as a variable? So time is on the bottom of the equation, so it's a little tricky to isolate. But I'm going to multiply both sides actually by distance to get rid of it, which gives me this really, really wonky equation that speed divided by distance is equivalent to 1 divided by time. What's fun about fractions is if you just flip them over, they can still work the same in terms of their ratios. So if I flip both of my sides, then I can get a simplified equation that tells me time is equal to distance divided by speed. So let's review these 3 equations. You must know these 3 equations. I will typically give them to you, or you'll have them in your notes when we're working on equations, but keep these handy as we begin to solve speed practice problems. So if speed, let's do some examples. Speed is equivalent to distance divided by time. Let's say we're solving a word problem and I give you a distance of 50 miles. In a time of 2 hours, I would calculate that speed is equivalent to 50 miles divided by 2 hours, and I would get my speed to be 25 miles per hour. If I'm solving for distance and I'm given speed and time in this example, speed is equivalent to 100 kilometers per hour, time is equal to 2 hours, then I'm going to use my equation that distance is equal to speed times time. And actually, if you look at our dimensional analysis and you include our units, I say distance is equivalent to 100 kilometers per hour times 2 hours. Whoa, the hours cancel, and I'm left with my unit for distance. So 100 times 2 is 200, and I get a distance of 200 kilometers. Lastly, let's say I'm solving for time. Time is equivalent to distance divided by speed. If I'm given a distance of 75 kilometers and a speed of 25 kilometers per hour, let's plug those into our equation. Again, the units work out. When you divide kilometers divided by kilometers per hour, the kilometers cancel out, and you're left with whatever, so you do 75 divided by 25. If you're looking at the units, that would be like looking at 1 divided by hours, which just completely rearranges to just get the unit for hours. So I get that time is equivalent to 3 hours. So we are going to practice this today, utilizing these 3 different equations, isolating a variable, and solving for one of the variables using these speed equations. So if you can flip your paper over, we're going to do the first practice problem together. So it's on page 78. You're going to work through these today in class, and let's get started. So, how we do these practice problems, one of the main things that we do when you are reading a word problem is there are 3 things that I want you to identify. When you read the problem, I want to tell you to tell me what are your known variables. I want you to tell me what are your unknown variables, and then I want you to tell me what formula you're going to use. Please use this process for all of the practice problems that we're going to be doing in class today. You're going to have to write down known, unknown formula, and then you're going to show your work. So this is how you should be showing your work when you're doing these practice problems in class. So number 1 says, Mr. Pryor runs 20 miles in 2 hours. Wow! Mr. Pryor can run really fast. So I want to know how many miles per hour is Mr. Pryor running. So when I look at this problem, there are 2 pieces of information I'm given. I see 2 numbers. I see that he runs 20 miles. Now that sends off like a little light bulb in my head, and I look at the unit for miles, and I say that's a distance. Then I look at in 2 hours, hours indicating to me that that is a time. So I have a distance of 20 miles and a time of 2 hours. Those are my known variables. Then what is my unknown? What am I looking for in this problem? The problem says how many miles per hour. Okay, miles per hour. I've heard of that unit before. That's the unit for speed. So I want to know the speed at which Mr. Pryor is running. Then I'm going to list what formula do I use to solve for speed. Well, speed is equivalent to distance divided by time. So if speed is equivalent to distance divided by time, I'm actually ready to show my work and plug in my number values. So speed is equivalent to 20 miles divided by 2 hours. So then if I do 20 divided by 2, I get that our speed is equivalent to 10 miles per hour. What's really important when we're showing our work for Mrs. Zaring's class is that we circle our final answer to indicate that that is the final answer that we are coming to. So if you would please pause this video and join the class to practice problem number 2 all together. Please share out loud and help out Ms. Castengren as you all talk together about this as a class. Okay, let's talk about number 2 together. So number 2 says Sally is driving to Moab, Utah. She pulls into a rest stop after 2 hours of driving. Her odometer indicates that she has a distance of 140 miles. What is the average speed that Sally drove? So my first step is to list my knowns. I know that the distance that Sally traveled was 140 miles. I also know that she traveled that distance in a time of 2 hours. The unknown in this case is the speed. I know that because it asks what is the average speed Sally drove. Lastly, I'm going to list my formula. The formula that I use is speed is equivalent to distance divided by time. So her speed would be, if I plug in my values, 140 miles divided by 2 hours. When I do 140 divided by 2, I get 70, and my unit for speed is miles per hour. And then to finish solving this problem, I circle my final answer. So for the rest of class today, with your classmates, either online or in person, you are going to work together to solve problems 3, 4, and 5, and then you'll go over the answers all together at the end of class. So good luck with this. Please utilize your teacher if you have any questions, and thank you so much for listening.